Assalamu alaikum wa rahmatullahi wa barakatuh. This is the last video of part 1 of chapter 10, Alternating Sinusoidal Current. At the end of this video, you should be able to explain the phenomena of charging and discharging of a capacitor under constant voltage and under square voltage, and determine the expression of the energy stored in the capacitor in the RC series circuit. First, let's remember some of the concepts from the previous video. 1. Differential equation in voltage UC across the capacitor during discharging is UC over RC plus DUC over DT equals 0. 2. The solution of the differential equation is UC equal E exponential minus T over tau. 3. At T equal tau, the capacitor charges reach 37% out of the maximum charge Qm. 4. At T equal 5 tau, the capacitor charges reach 0.7% out of the maximum charge Qm. Practically, the capacitor is totally discharged. Watch the following video, which contains an experiment that explains the charging and discharging of a capacitor under a square signal.
Okay, so resistor, so from generator to resistor to capacitor to other resistor to negative on the power supply. So let me put this to simplify the connections with the oscilloscope. One here for the positive rail where the generator is located, and this is the ground rail instead. Okay, so for this circuit I'm gonna use this device here, which is my generator, in which will basically create a square wave. I will use this function generator to charge and discharge the capacitor with a square wave, and then we will see the information coming out on the oscilloscope, channel 2 on the oscilloscope to the capacitor, so ground side and other terminal of the capacitor. And I will use the other channel of the oscilloscope, channel 1, between the positive rail, which is basically the one that will be powered by the function generator, and ground again. And then I will attach the connector of the power generator between this point, which will provide the voltage to the capacitor, and ground again, which we can put it over here. So we can see the yellow one is the generator that powers the capacitor, and the blue trace is the charge cycle over here and the discharge cycle of the capacitor over here. You can see that when the voltage is applied to the capacitor starts charging very quickly at the beginning, and then slower and slower and slower until it reaches the maximum charge. Conversely, when we short the wires of the capacitor will initially discharge very quickly, and then slower and slower and slower until it is totally discharged. Let me disconnect here the oscilloscope from the capacitor, and let me connect it on this resistor so we can measure actually the current that flows into the capacitor. Here we go. Let me overlap these two lines so we will see exactly what happens. You see again, the voltage is given by the yellow line, and this is the power supply for the capacitor, and the blue this time is the current through the capacitor. You can see at the very beginning, since the capacitor is totally discharged, there will be the maximum difference of potential on the resistor R1 that we saw before, so there will be the maximum flow of current, which will shut up to the maximum possible imposed by the resistor. Then, while the capacitor keeps charging, the current will start reducing until it goes to zero entirely. This is when the capacitor is completely charged. Conversely, when we short the capacitor, then there will be a peak of current in the opposite direction, because now is the capacitor that is moving the current across the resistor in the opposite direction, and we will see over here. And then the current will keep going until it reaches zero, when the capacitor is completely discharged. Let's compare now directly the voltage of the capacitor and the current of the capacitor. The channel where I measure the voltage from the generator directly onto the capacitor. Let's go back. Let's see what happened here now. See, now the yellow line is the one that represents the voltage across the capacitor. The blue line is the one that represents the current across the capacitor.
Energy distribution in an RC series circuit under a constant voltage. The following circuit contains a neutral capacitor of a capacitance C, a resistor of resistance R, and a switch are connected in series across a generator of constant voltage E. At t0 equals 0 second, the switch is closed and the charging process starts. During charging, the generator is delivering energy to the circuit, while the capacitor is storing electrical energy and the resistor is converting the electrical energy into heat. Knowing that the instantaneous power of any energy converter is P equal to the derivative of the energy with respect to time. Expression of the electric energy stored in the capacitor. Knowing that P equal dW over dt equal I multiplied by UC, where UC is the voltage across the capacitor, while I represents the electric current traversing the circuit, then dWC equal PC multiplied by dt, which is equal to IUC dt. Then WC, the energy stored in the capacitor, is the primitive of the instantaneous power. That's mean WC equal integral IUC dt. And as we know from before, I equal dq over dt equal C duc over dt. So we can replace UC by I by C duc over dt. So then the expression will be integral of C duc over dt uc dt equal to integration of C uc dc. That's mean the answer of this integration is equal to half C uc square plus a constant. And we can find the value of the constant by replacing the values of UC and WC at t equals 0. And as we know, at t equals 0, the capacitor is still empty. So the voltage across the capacitor UC is equal to 0 and WC is also equal to 0. Then after replacing UC and WC in the expression of the electric energy, we can conclude that the constant is equal to 0. Then the expression of the stored electric energy is given by WC equal half CUC square. And as we know from the previous video, UC is an exponential function. So WC is an exponential function also, and we can use this expression for the electric energy during charging phase and during discharging phase, where WC is also depending on C and UC. The following table contains the differential equations in UC, Q, I, and UR and their solutions during charging phase. For UC, its differential equation is equal to E over RC equal UC over RC plus DUC over DT. And its solution is UC equal E multiplied by 1 minus exponential minus T over tau. For Q, the differential equation is E over R equal Q over RC plus dQ over dt, and its solution is Q equal Qm multiplied by 1 minus exponential minus T over tau. For UR, the differential equation is 0 equal UR over RC plus DUR over dt, and its solution is UR equal E exponential minus T over tau. For I, the differential equation is 0 equal 1 over RCI plus DI over dt, and its solution is I equal Im exponential minus T over tau. The following table contains the differential equations in UC, Q, I, and UR and their solutions during discharging phase. For UC, its differential equation is UC over RC plus DUC plus DT equal 0, and its solution is UC equal E exponential minus T over tau. For Q, the differential equation is Q over RC plus DQ over DT equal 0, and its solution is Q equal Qm exponential minus T over tau. For UR, the differential equation is UR over RC plus DUR over dt equals 0, and its solution is UR equal E exponential minus T over tau. For I, the differential equation is 1 over RCI plus DI over dt equals 0, and its solution is I equal Im exponential minus T over tau. Summary. The expression of the stored electric energy in the capacitor is given by WC equal half CUC square. This is the end of part 1 of chapter 10, Alternating Sinusoidal Current. Study well and thank you for your attention.